What if I told you that the entire foundation of calculus, all of its power to describe motion and change and space, could be understood with a question so simple you can answer it with just a pen and paper? Well, today, that's exactly what we're digging into. We're exploring that foundation, continuity. So let's get right to it.
All right, so let's start with that question. And I want you to forget all the formulas just for a second. Seriously, just picture yourself drawing a line, a simple curve on a piece of paper. That one physical act, that's actually the key to unlocking this whole idea of continuity. And that simple idea, that drawing motion, it gives us our starting point. We're going to call it the pen test. Before we even think about touching the complex math, we're just going to build up this gut feeling, this intuitive sense for what continuity is all about.
So here it is, the pen test in a nutshell. If you can draw the graph of a function in one single smooth motion, without ever lifting your pen off the paper, then it's probably continuous. Yeah, it's really that simple to start.
Okay, so now we can put an official name on this idea. Any function that passes our little pen test, that's what we call a continuous function. Think of it as just a smooth, connected path. There are no breaks, no weird gaps, and definitely no sudden jumps. It's just all one piece.
But, a gut feeling isn't quite enough for mathematicians, right? They need precise, official rules. So now it's time to level up. We're going to move from the simple pen test to the official definition, which is actually a lot easier than it sounds. We can just think of it as a simple three-point check.
And here it is, the formal definition. Now, don't let the symbol scare you. All this is really saying is that where a function looks like it's going is exactly where it actually ends up. So in math speak, the limit of the function as you get super close to some point A has to be the exact same as the function's actual value at that point A. No tricks, no last-second surprises.
So we can break that one big rule down into this awesome, super simple checklist. Okay, ready? Number 1, does the point even exist? Like, is f of a real defined thing? Number 2, does the limit exist? Meaning, are you heading to the same spot whether you come at it from the left side or the right side? And finally, number 3, do the point and the limit actually match? If you can say yes and check all 3 of those boxes, boom, the function is continuous at that spot.
All right, so what happens when a function fails that three-point check? Well, that's when you get something called a discontinuity. And there are basically 3 main ways a function can break. You get these breaks, jumps, and holes. Let's go through each one.
Okay, our first case is the sneakiest one. It's pretty subtle. I want you to imagine a perfectly smooth stone path, but one single paving stone is just gone. You can see exactly where it's supposed to be, right? The path leads right up to the empty spot from both sides, but the stone itself is just missing.
In math, this is called a removable discontinuity, and it fails our checklist on point number 1 because the point f of a isn't defined. There's literally a hole in the graph. But, and this is super important, the limit does exist. Both sides of the path totally agree on where that missing stone should have been.
Okay, now for something a bit more dramatic. We're not talking about a little missing stone anymore. Think broken bridge. You're cruising along a road, and all of a sudden it just drops off and picks back up again way higher or way lower. There's this huge gap you just can't cross. Yep, this is a jump discontinuity. And this one fails our checklist because the limit doesn't exist. Remember rule number 2? The value you're heading toward from the left is completely different from the value you're heading toward from the right. The 2 sides of the bridge they don't line up at all.
And that brings us to our final case, which is by far the most extreme. This isn't a hole, it's not a jump. This is like the path you're on suddenly leads you to the edge of a giant canyon. The function just goes completely haywire.
We call this one an infinite discontinuity, and it fails our checklist because as you get close to a certain point, the function's value just skyrockets up to infinity or plummets down to negative infinity. On a graph, this creates what's called a vertical asymptote, that invisible wall that the function gets closer and closer to, but can never ever touch.
Okay, so we've seen what continuity is, and we've seen what it isn't. But the really big question is, so what? Why do we care? Why is this one idea so unbelievably important? Well, it turns out it's pretty much everything to calculus.
And I am not exaggerating here. You really can't overstate how important this is. Continuity isn't just some helpful side concept. It is the absolute bedrock. Without it, the whole structure of calculus, it just comes crumbling down.
Here's why. The 2 absolute power tools of calculus, Differentiation, for finding slopes, and integration, for finding areas. They both require a smooth, unbroken path to do their job. I mean, think about it for a sec. How can you possibly find the exact slope of a curve right at a point if at that point there's a hole or a giant jump? You just can't. The whole system completely breaks down. And that's really the big takeaway here. Continuity is our guarantee. It's the promise that a function is well behaved, that it's smooth and predictable enough for us to apply all those powerful tools of calculus to it. It's the thing that lets the magic happen.
So I'll leave you with this final thought to chew on. We tend to think of our world, things like time and motion and growth, as being perfectly continuous, perfectly smooth. But where do these mathematical jumps and breaks actually show up in the real world? I mean, think about the very instant you flip a light switch from off to on, or the sudden jarring jump in a stock price. What other real-world discontinuities can you think of? Something to think about. Thanks for joining me.